Hello and welcome to tutorial 6 of the platemaker wizard. So we'll click on Excel, we'll go add-ins, help, and interesting enough the version I'm running now is the non-commercial version. This is the academic version. Some of the earlier tutorials I was running the commercial version, so you'll get to see the difference on page 1. We want to open the instruction manual, so I'll click View Instruction Manual. And we go down until we get to tutorial 6, which is here. So tutorial 6, it covers page 4 of the wizard, where we were looking more at equations, derived equations, combining measured variables to create our own equations. We also looked a little bit of this in the last tutorial when we were looking at plate controls, but this is a further exploration of page 4 functionality. However, as we move towards the final tutorials of the wizard, we are going to refresh ourselves on some of the earlier stuff. So remember tutorial 2, we covered page 1 of the wizard. We're going to cover page 1 of the wizard again a little bit, in that we're going to actually save this particular workbook. And when I was doing page 1 of the wizard before, we were using the commercial version of the software. Today we're using the academic version of the software, so the folder structure is a little bit different for the academic versus the commercial version of the software. So let's do this. So we go back, we can close this window, and now we go platemaker, create new data entry workbook. We want to save the file as the exercise, so we click Save File. This will automatically add it to the experimental register. If you're doing this exercise yourself, you probably want to untick this option because you don't want to be putting practice workbooks into your experimental register, especially if you are using the platemaker wizard or your lab is using the platemaker wizard to make real workbooks for your lab. But given that I am just showing you how to use the platemaker wizard, I will leave this option ticked. So as soon as Save File is ticked, these boxes as described before become drop downs, and these first 3 drop downs control the subdirectories that are created in the platemaker wizard data directory where the workbook you're about to create will be saved. So you can see the first drop down is project name, and you can see in our examples we have different project names. What we're going to do is we select tutorials, because this is obviously a tutorial. So we select tutorial. The project manager, that would normally be yourself, or it could be somebody else if there's somebody managing the overall project and you're the experimentalist. So in the instructions you will see it says to enter your computer login name. However, I'm going to enter Jack Ripper just for the fun of it, so he can be the project manager. The experimental title, so if you follow the instructions, we're going to call this Elisa time course experiment. So let's type that, Elisa time course experiment. And the media used is DMEM, so let's type DMEM, it's already in there for me. The well contents is cell lysates, cell line lysates. And I've also put in comma, please see plate map for details. Let's type that in. The experimenter name can be myself, Rod Benson. The experiment duration is, and again this is a multiple duration experiment, so we're going to select see plate map for details. Now we come to the sample numbers. Now this is an ELISA assay, and the design of this ELISA assay is we're going to measure the phosphorylation of EGFR receptor in one ELISA plate and the total amount of EGFR receptor in another ELISA plate. So given there are 2 different plates, there is no relationship between the plate replicates, so rather than using sample numbers, we're going to use each measurement is the mean of 3 plate replicates. We need to type this, so it says EGF time course assay with 3 different cell lines. The EGFR dose used in all wells was 100 nanograms. Let's type that. So EGF time course with 3 different cell lines. The EGF dose used in all wells is, okay, the EGF dose in all wells was 100 nanograms per mil. Okay, so if you wanted to, you could actually save that as an independent variable, but if the independent variable EGF dose is just a single value, you don't really need to include it in the flat data table. You can just include it here because it's not changing, and you can just make it as part of the notes. So the choice is yours, but I'm going to save it in the other relevant notes section. So now we come to the date section. So we could select today's date. I'm going to actually select the date that is in the tutorial. So it's the 9th of the 9th, 2024. So let's do that. So I'm going to use the calendar key. So I click the calendar key. I want to go back to 2024. I want to go to September. And I want to go to the 9th. So that was a Monday. And there it is, 9th of the 9th, 2024. The cell confluency, it says, is 90%. So I put 90% in. Oh, in fact, actually, it's the 2nd of the 9th that I want, not the 9th of the 9th. So let's go back and put it as the 2nd, which is also a Monday, a week before. And then I just click Add Experiment, and there you see it's in there. Okay, so we have now entered all the information on page 1 of the platemaker wizard. If we move down through our tutorial notes, there is a small paragraph which explains why we put the EGF dose into the other relevant notes sections and not bothered to actually put it on the flat data table because it's only one value. So you can read that, and now we're ready to enter the information on page 2, the independent variables. Now we have 2 independent variables. We have cell line and time. So let's do that next. So we switch over to our wizard, we click next, and we type in cell line and time. The cell line is a text variable, and the 3 values are PC9, healer, and STC1, and I'll use the dash in the STC1 name this time. The time dimension is in minutes, and the time points are 0, 1, 2, 5, 10, and 30. So we enter those, and you can see that here. So there's the 2 things we've entered. We're now down here. We've entered these successfully. So we're ready to move to page 3 and enter our dependent variables, which is the 2 ELISA assays. So this is phospho-EGFR, tyrosine 1173, and total EGFR. So let's do that. So we go next. And the first one we want to enter is phospho EGFR, and it's tyrosine 1173. Now, one thing to note, remember that when you type in information in a list box, it'll pick up other things that are in there that start with the same letter. So you notice I was trying to type capital P, but it's now replaced with little p. If that happens, you can simply change it back to a capital P. I want that as a capital P. You'll see it happens here because I want nanograms per mil, but as soon as I type N, I'm going to get number because nanograms per mil is not in there yet. So I'm just going to ignore that and type NGML, if I can type. But then what I'm going to do is I'm going to change the big N back to the little n, just to make it correct. So that's the way you get round if it's auto-completing and it's putting a capital in, you want a little one. You just change it after you've typed the new label. Okay, so we'll enter that one, phospho-EGFR. And then the second one we want to enter is total EGFR. And again, that's nanograms per mil. So this time we're doing a full calibration. We're using a full standard curve. So we go enter. Now, because this is an ELISA assay, we also want to use a dilution factor to match it to the standard curve to actually do the calculations backwards, so we end up with nanograms per mil. So what I'm going to do is I'm going to put my cursor on the phospho-EGFR. I click Use Dilution Factor. In the instructions, you'll see that the sample volume, that's the volume we're adding to the well, is 5, and the total well volume is 100, and it's microliters. So I click Edit, so that gets recorded there. And I need to do the same for total. So it's exactly the same. Use dilution factor, 5 and 100. Now, interestingly enough, you can see that we also have this drop-down menu of microliters and mils. So if I put this to mils and I put 0.1 mil, it would be exactly the same, and the computer program is clever enough to put in the SI conversion unit in the calculation, so it does all that for you, which is quite cool. So I click edit. So now you can see that both these are now using a dilution factor, as you can see. And we keep going. So we're down here. We're not going to use any controls, so we just simply click next to get to our equation editor. And now the equation we're going to do is a nice simple ratio of these two. So let's do that. So we're going to call this PEGFR ratio. And now the equation, we simply select our first available variable, phospho-EGFR. So we click on that, it puts it in there nicely. We then want to divide. We can use the divide key here. And we click on this one, total EGFR, and there is our ratio. So we click add, and it goes in there. The second one we want to add is a demo. So this is just showing you can now use this equation. You can define new equations based on previous equations. We're just going to call it demo. It's just the ratio, but we're going to multiply it by 2. So let's do that. So we just type in demo, and it's just ratio again, and it's just the new variable PGFR ratio. We use the times key, so I can use this one here if I want to, times, and then it's just 2, and we click add, and now we have our 2 equations in if you're following the instructions. So we now go to page 5. So we're now on page 5. So the first thing we need to do is change the layout direction from rows to columns. So let's do that. So now it's by rows. And now what we want to do is we want to change the number of rows from 8 to 6. We don't have to untick the leftover space. This is explained in the instructions, so we leave that ticked. We click preview. And if you've done everything correctly, you should end up with this plate map, which we do. So now I'm going to click accept to accept the workbook, and you can see that now, because we set up page 1 with all the information, we've actually saved the workbook. You can see it's saved, so it's actually been saved to the PC, and we'll go through that in a little bit. So before we do that, let's now go to the flat data table and just see what it's done with those 2 equations. So we're going to go to the flat data table, and it's asking us to set up some filters. So we need to set up the column filters PC9 and 30 minutes. So let's do that. So we go to the cell line, we're going to select PC9, we're going to select on the time course 30 minutes, which is that one, and we end up with this small subtable here. And now we're just going to go to PC9 PGFR ratio. If I click F2, you can see what it's done. So you can see how the formula is working here. Now remember, we use repeat numbers, so it assumes there's no relationship between phospho-EGFR and total EGFR in terms of the sample numbers because they're on different plates. So it's correctly meaned the 3 values for phospho-EGFR coming from the phospho-EGFR ELISA plate. It's meaned the 3 values of total EGFR coming from the total EGFR ELISA plate, and it's calculated the ratio, as you can see here, average divided by average. Likewise, we have this single demo ratio, and that is, if we click F2, is simply our PGFR ratio multiplied by 2, because that is what we set up on in the equation editor. If we go to the experimental details, you can see our 2 derived variables are also shown in our experimental details page under description. There they are there, so you can see what we've done there as well. Remember, we also used a dilution factor, so let's look at that as well. So what we're going to do is, if we go, say, and look at one of these values here, you can see that the formula is quite tricky. So if I go to the phospho-EGFR page and D11, let's just do that, you can see that D11 is correctly our PC9 30 minutes repeat 2, but you can see that C3 is the 5 microliters and C4 is the 100. So what is effectively done, again, is it's got D11 and it's C4 and then it's divided by C3. So it's actually doing the ratio. So it's correctly converting the dilution factor on the plate in the flat data equation. So it sorts this out for you if you do use a dilution factor, as we have done on page 3. And that is described here. as you can see. So just read this section so you understand it. Note also it uses the if is number, and that's just to make sure to keep the flat data table clean. So if there is no information in these wells, then there's no information appears here. In fact, let me just enter some information so you can actually see it go in. So if I was to put in a value, let's just put a value. So we put in our value, it's here, isn't it? D11, I think it was D11. So if I put in the value 20, say, then if I go to flat data file, you can see now that it's correctly taken into account the dilution factor. And in fact, if I do the same with the total EGFR, so let's do one for total. Let's put in a total of 12. Then you can see that now it's also calculating the ratio and the double ratio. So you can see it's all working very well. So we're now going to look at a much more complex dependent variable equation. But before we leave this section, I also just want to cover where this workbook has been saved. And also remember, I want to cover the experimental register. This is the academic experimental register. So what I'm going to do is I'm going to close this workbook. I will save it. And now what I'm going to do is I'm going to reopen Excel. And this time we're going to open up the experimental register here. This is the academic version of the experimental register. We've already seen the commercial version in tutorial 2 of the platemaker wizard. This is the academic version. And you can see it's a simpler one than the commercial, which have projects, workbooks, and staff. If we go to projects, we know we've saved everything in tutorial. So we just go to tutorials, and there is our Elisa time course that we've just saved. If I open that, you can see this is the notes, the testing science. Remember, the project manager was Jack Ripper, and we just open the workbook. And there's the workbook. You remember that's the filter we had on. That's the data we just entered. You can see the plate maps. If we close it, we can also open the folder path. And there's the file. You can see it's saved here. So there's the public directory under, so we have platemaker wizard data. There's documents, platemaker wizard data. Then we have the projects. In the projects, these are our different projects. And then under tutorials, under Jack Ripper, and under Elisa time course, and there it is. So you can see it all working very nicely, the experimental register and the platemaker wizard, keeping track of all the different experimental workbooks you build and keeping them all organized in your file server on your computer or on your local computer. So again, that's the power of the platemaker wizard, to keep everything organized as well as you build your different workbooks. Okay, so we've done that. We're now going to move on to our next section, which is using control data in your dependent variable equation. So let's do that. So we're going to reopen Excel. This time we need to put the program into tutorial mode. And now you can see, following on from our instructions, we're going to select tutorial 5 first workbook build. So let's do that. So we go down to here, create new data entry workbook. We want tutorial 5 first workbook build. We want to adjust the template settings. We click next. You can see it loading the data. Next. These were the plate controls. Next. And you can see, if you remember when we did this on the last tutorial, we did create different equations. We had cell count adjusted, which is just cell count minus average DMSO. Cell depth adjusted, which was cell depth minus average DMSO. And of course we just have average DMSO because that is being recorded here. So the first thing we want to do is we're going to delete these 2 equations because we're going to replace them with more complex equations. So let's do that. So if I just click on one of these, it instantly adds it to the box, which is what I don't want to do. I want to delete. So in order to delete something, the way I do that is I have to push here delete equation. So it tells the menu that you want to actually delete something from here rather than just add it to your equation text box. So let's do that. So I click the delete equation, and now you can see a delete button has appeared, and now I can just select the ones I want to delete, which are these two, and I click delete, and the formulas are gone. If I try to delete a dependent variable, you can see it won't let me do that because I have to delete that on page 3 of the wizard, which is what it says. Okay, and if I try and delete an equation that has equations dependent on it, it also won't let me do that. That is all explained here, so you can read all of that. Now we're going to add a new equation, and the new equation we're going to add is going to be similar to this one. But first of all, let's just look at the equation that we use in the demonstration workbook. So it's cell death normalized. And the way it works is it starts by simply taking cell death, subtracting the background control, which is what we did with our adjusted equations just a moment ago, very simply. But then it rescales, and the way it rescales is it rescales by then subtracting cell death control from 100 and multiplying by 100. So this means that anything that was 100% originally will become 100% again after cell death control has been subtracted. So that's the first formula. But the problem is that formula, if it turns out that the cell death in the control is higher than the cell death in the treated sample, then you'll end up with a negative number. So we don't want that. So this is where we use an Excel logical test to make sure that if the number is negative, it puts in 0 to stop getting negative numbers. Okay, so that's what we're going to do. So that's the equation that we use in the demonstration workbook that's shipped with the platemaker wizard. But for this example, we're actually going to make it even more complex. So this equation, what it would mean is it would mean that 100% would only be 100% if it was 100% before the cell death control was subtracted. But what we want to do now is we want to rescale against the positive control so that the maximum positive control when it's in cell death normalized will always be 100%. So we're going to use a slightly more complex formula shown here, and this is the one we're going to enter. So in order to do this, we need to tell the platemaker wizard on page 3 to calculate the maximum cell death for the positive control. So let's do that first. So first of all, we go previous. This is the positive control, remember, benzothenium chloride, and we want it to now calculate the maximum. So you can see it now says calculate the maximum. We go next, and now you can see we have the maximum benzothenium chloride as a variable that we can select in our equations. So let's now work on our first equation. So our first equation is cell death normalized. It's a percentage. So now we begin. So the first thing we're going to do is remember we also not only want this more complex equation, but we also want to make sure that if the cell death value is less than the cell death control, we don't get a negative number, we get 0. So we also want to bring the if statement in. So let's all do this now. So how we do this is we type if, because remember we can use the if statement inside Excel, open brackets, and now it's going to be if cell death is less than the average control, then we want it to just read 0. If it's not, then we begin our equation. So our equation is cell death minus the average negative control, and we need to put that in brackets. So let's go back so we can follow it here. Okay. And then we need to times that by 100. So we times that by 100. And then we're going to divide it. And if we were doing our simpler equation, it'd just be 100 minus average DMSO. But now, instead, we want to scale so that the maximum positive control is set to 100 in this equation. So to do that, we say the maximum benzothenium chloride minus, again, the average DMSO. And again, this needs to be in brackets because we need to do that subtraction before doing the division and multiplication. Remember, order of operation. And then the final thing we need to do is we need to add one more close bracket, because remember that's the outer bracket for the if statement. You can see that in red. So that's the equation. If you've done it correctly, you then push add, and if you've done it correctly, it should just enter into your box like so. If you make a mistake, the program should give you an error, and I'll show you that in a minute when I do the next equation. So we've entered our first big equation, cell death normalized. So let's keep going. Now we also want to enter a cell count normalized, and what we're trying to do with cell count normalized, so just to explain, what we're trying to do is, a lot of anti-cancer drugs, not only do they cause cell death, but they also stop cell division, so they cause a drop in cell number. So we also want to measure how the cell number has decreased. But the final thing we're working towards is an equation called cell demise, where we average the cell death and cell count. Now obviously the cell count is going to decrease when you add an anti-cancer drug, and the cell death is going up. We want them to move in the same direction. So what we do is we use this interesting cell count formula, which basically starts with 100 and then subtracts the decrease in cell count. So as cell count gets less and less, this approaches 100, which is what we want. If cell count is the same as the average cell count control, then this becomes 0. So it's moving in the same direction as cell death so that we can average. Okay, so it's kind of flipping everything around. And the original formula that we used was this one, which is quite a simple formula. And what that would mean is that cell count would have to go fully to 0 in order for this to be 100%. But the modified formula, the equivalent modified formula we want to use now, is we want to make sure that the maximum positive control, so in other words the positive control that has caused the biggest decrease in cell number, equals 100%. And this is where we're now going to use our second variable. We want the computer to calculate the minimum positive control count so that we can use it in our equation here. But we also need to throw in the if statement, so that if the cell count of the treated sample is less than the average negative control, we code that as 0 so that we don't end up with negative cell count normalized numbers. So you can see it is quite a complicated equation. Now you should read note 23. We never did this calculation when we were doing this for real because we're using benzothelium chloride, and benzothelium chloride, interesting enough, does not cause an arrest in cell count. In fact, cell count goes up in the positive control, and the reason why is because it causes cell fragmentation, that particular treatment. So if you're going to do this for real, you'd have to use a different positive control that causes cell count arrest, just like an anti-cancer drug. So again, this is not real experiments, this is just teaching you how the platemaker wizard works. The other problem is if you use this more sophisticated equation, you could also end up with other problems where you end up with cell count normalized that is greater than 100% if your negative control is causing an increase in cell count. So as I say, these exercises are not meant to be strictly related to the biology of the experiment. It is more just teaching you the different functions of the platemaker wizard, and I want to stress that so that you don't get confused and think, hang on, this doesn't make sense biologically. Okay, so with that said, let's recreate this complicated formula. So we're going to do that. If you wanted to cheat, actually, you could just literally copy this formula straight in and it will just work, but let's do it manually. So we're going to call this cell count normalized. Again, it's a percentage, and it is. Let's do it. So the first thing we need is if we want to test if cell count is greater, so this time it's greater than the average DMSO control, then in that situation we want it to just be 0. However, if it's not that, then we start our equation. So it's 100 minus, now you see what I've done here, I've forgotten to ask, I need the minimum benzothelium chloride. So before I do any of this, I need to go back and get the minimum benzothelium chloride. So let's do that. So I'm actually going to go previous. So you can see now I've got a mistake in my construction. I never finished that formula, so that's fine. And I'm going to go benzothelium chloride, and I need to also calculate the minimum. So I click that. And now you can see I have my minimum available. So now I can start the equation again. So it's cell count normalized. It's percentage if, open brackets, and the first thing we need to test is cell count is greater than the DMSO background. Then we want to code that as 0. If not, we start our equation, and our equation is 100, and then we subtract off that, and it's going to be cell count. And remember that this time we also are going to subtract the minimum positive control count. So we're going to subtract the minimum benzothenium chloride, and this has to be bracketed because obviously this is a separate part of the equation, so we want to bracket that because we need to do that. Once that is bracketed, we're then going to times that by 100, so we times that by 100, and then we divide by the average DMSO minus, and again it's the same thing, minus, and it's the minimum benzothenium chloride. Again, we need to bracket that part as well so that it gets, before it does the division, so we get the proper ratio. And the final thing we need to do is we need to put the second bracket in to match the first bracket. Again, if I don't put it in, it'll give me an error. Let's now put the second bracket in to match the first bracket of the if statement. We click add, and if we've done it correctly, it should just drop in, which it does. So now we've entered our second equation. And then finally, our last equation is cell demise, and this is a nice simple equation to finish off. So it's cell demise, it's percentage, and it's just the average of cell death normalized plus cell count normalized, and we need to divide that by 2, but remember we want to add before dividing by 2. We need to change the order of operations, so we do need to put a bracket divided by 2, so it's just the straight average. We click add, and there's cell demise, so we'll put that in. And now our page 4 should look like that, which it does, so everything's correct. We push next, and we can push finish straight away, so let's push finish, build the workbook, and there's our lovely plate maps. And now what we're going to do is we're actually going to import our tutorial data so we can just do some final looking at the flat data file to really see what's going on. So let's do that. So we're going to go back to the flat data table. We're going to import data. So let's go to our file explorer, documents, shortcut, platemaker wizard data, tutorial. We want import practice data. And in our tutorial this time we're going to open plate 123 just to give us some more practice at importing data using the generic importer. We click open. We'll now open those 3 data tables. Being a bit slow, but there they go. Okay, it's got them open. We now go add in. We go import data. It's picked up plate 1. We need to make sure that it's at B2. So remember, I could just type B2, or I can right click. Let's right click and put it on B2. There we go. So that's in. We're now using multi-source and read. So we're going to use multiple workbooks, remember. So we're just going to click workbooks. We're not using rows between plate, and plate 1 is in. So we now need to add plate 2 for plate 2, plate 3, plate 3. It's also import multiple readings. We need to match up, so this time they're worksheets, because remember this is cell count, cell death, so we use worksheets. Cell count to cell count, cell death to cell death. We want to close the source workbooks after import, so we tick this box. We click import data, and it all goes in nicely. So now you can see we have our cell count data in, we have our cell death data in, and we have our flat data file fully populated. So we've done that. So now we go back to our tutorial, and the final thing that we're going to do is we're going to select these compound filters. So the first set we're going to do is following figure 116. We're going to set plate number filter 2. So let's do that. So we go plate number filter. We're just going to select plate 2. Then we're going to select compound filter all the benzothenium chlorides. So let's do that. So we're going to go all the benzothenium chlorides. and there's 3 of them, so you can see the raw data, then we have the max and min which we asked to calculate, so we do that. And then the final thing we're going to do is select cell count and cell count normalized. So let's do that. So we're going to go cell count normalized, and we get this little table here. So we've done all that correctly. So what we're going to do now is we're just going to look at some of these numbers. So just to show you how it's working. So you can see that if we look at the cell counts, you can see that the numbers are 586, 532, 586. The minimum number is here, is 532. Do you see that? So that is the minimum number in blue. And the maximum number is number 5610. And so therefore you can see the calculator has correctly picked up the minimum because it's using the minimum, so it's picked up the 532, and the maximum has correctly picked up the maximum, which of course is 586. Okay, so that's fine. Now this is the derived formula. So if we look at the derived formula, do you remember we wanted the minimum to equal 100%, which it now does. So you can see our formula, which is incredibly complex, is actually working. Okay, so it's picking up the 100%. It's also got the DMSO background, but you can't see that. In fact, I could bring that back in. Let me just add an extra filter. If I bring in the DMSO average, you can see that now you'll see that you can see it's referring to the DMSO average there. Okay, so on plate 2, so you can see it's picking up all the right values of plate 2 to come up with that 100%. And interestingly enough, the other one we remember was the maximum was sample number 5. So if I go to sample number 5, that you can see now is the minimum because the cell count formula is flipping everything around. So that's how it's working. So that is kind of showing you how the formula we've created is correctly working. Now you can see that actually, because these formulas here are derived not from minimum maximum but from the derived formula that we're using here, they're now actually round the wrong way. But there's no need to worry about that because you're not actually ever going to use that data in your analysis, because remember that data is normally used inside your own formulas. There's no more formulas, so it doesn't matter that's round the wrong way, and most of the time it wouldn't be. It's just unusual because we're using a formula which is kind of inverting cell count, so it's reversing. So when cell count goes down, this formula is going up, which is now why it's round the wrong way on the derived formula. That's all explained in here if you want to read figure 117. So the final part we're going to look at is we want to now create a table in figure 119. So let's do that. So in the compounds, we clear all the compounds, we select benzothium chloride max, DMSO average, and capecitabine, which is there. We then want 0 and 100, so we select 0 and 100, which is there. And then finally, we want to take off all the dependent variable filters. So we want to select all, so they all come back. And we end up with that there. This little table here. And now if I read the instructions, I now need to place my cursor in cell G2483. So let's do that. G2483 is that cell there. You can see this is capecitabine 100 nanomolar sample 2. If I click the F2 key, you can see how that formula is being derived. So you can see it's picking up the DMSO average on plate 2, and it's picking up the benzothium chloride on plate 2, and obviously capecitabine, which is on plate 2. You can see that's the formula that we created is shown here to derive the value of 39.5%. So you can see it all working. That's described in figure 119. And in fact, you can also see if we go to the cell Demise that if we push F2, it's picking the cell death normalized from plate 2 and the cell count normalized and averaging them. So everything is working as expected. So that is described in figure 19. The other thing to read about, which is really important, is how the wizard knows which dependent variables controls to use. So this is really clever. If you think about it, we're only using the average DMSO label, but for cell count that needs to be the average DMSO for cell count, but for cell death it needs to be for cell death. And the way the algorithm does this is it works out which variable is being referred to and then picks the right one. If you did have two variables, so if you had cell count and cell death in the same formula, then whichever one is closest to the label, it will pick that one. So sometimes in that situation, although I can't imagine you'd ever create a formula like that, you would just have to be careful of the ordering so that it picks the right average DMSO because it's closest to the measured variable that it needs to match to. Okay, so that's explained there. The final section I'm not going to cover because in this tutorial in terms of the video, but just to point out that if you look at the demonstration workbook that's shipped with the platemaker wizard, the formulas actually are a bit more friendly. You can see that rather than using DMSO average, they're using average negative control. And the reason they can do this is because there's an extra variable in there called class. In fact, I will just open up one just so you can see it. Let's just do this. If I go to Help Demonstration Workbook, I can view the demonstration workbook. You can see that the formulas here are a little bit friendlier because they're using average negative control. And the reason they can do that is because this particular design had a class variable in it. So because I had the class variable negative control, I could use this in my formula rather than this column here, and that's why we have a more user-friendly sample. And you can see it being described how this happened. So this is the way we set it up when creating the demonstration workbook, but interesting enough, I could have set up the other way and just return to using the DMSO average if I put the class in the second column like this, or not use the class at all. So that's just being described here. Okay, so this is the end of the tutorial. So again, I hope you've enjoyed this. I hope you understand what we've talked about. I hope you appreciate the power of page 4 in terms of creating your own derived equations from your measured variables. If you did like this video and are watching it on YouTube, please do click the like button, and also think about subscribing to this channel so that more scientists can learn about the platemaker wizard and the incredible power this tool brings to analysing your microtiter plate experiments. Until tutorial 7, I wish you well with all your experiments and have a great day. Bye.